Imagine you're a small snail living in the rivers of New Zealand, and then, for example, a dragonfly larva comes and attacks you. In the case of Latia, the shell is not enough, so it came up with a unique defense mechanism. My PhD project focuses on two primary aspects. I wanted to find the source of this glowing defense mucus, and therefore I investigated the gland system of Latia. And I also wanted to detect the proteins present in the defense mucus and its biochemical properties. I also used the reference snail, neritoides, because this snail uses a different defense mechanism. I had the great opportunity to sample my snails in New Zealand, and then all the laboratory work was done in Vienna. So a typical day looked like I went to the histology lab, sliced my animal into sections, I dried them overnight, and the next day I stained the serial sections. With the sections I then made the 3D reconstructions with the software Mira. For sure I repeated this process many times with various methods and different animals. On the other hand, if I want to detect my proteins in the defense mucus, I went to the molecular lab and there I ran a gel electrophoresis. Snail mucus is undeniable one of the most promising biomaterials. I mean, it's known for regenerating skin or treating burns. There's a wide array of luminescent biopolymers, based on cellulose, for example. They are employed in optical and mechanical drug delivery or biosensor mechanical applications. These systems often use toxic luminescent components like cadmium, for example, which makes them less appealing for human-oriented applications. Understanding of the Latia luminescent mucus system can lead us to the understanding of this luminescent biopolymer. In the long term, this can provide us with an innovative adhesive with underwater bonding abilities. Biological adhesives have so much potential. We want to surround us with non-harmful material. And here's a material that can provide all of this and replace a more harmful one.